Okay, in the previous few videos, we have been looking at the frequency spectrum of noise, and we said that it's called the noise spectral density. And then we looked at how, depending on what the frequency characteristics of the noise are, you can distinguish between different types of noise, right? In this video, I wanted to talk about how um, if you put in a noise through a filter, what happens to that noise? Okay, so here it goes. So when you pass a noise through a system, okay, let's say you're passing a noise through a system. The basic idea is that the spectral density of the noise changes its shape. Now, how does that happen? So let's say the transfer function of your system is A. Okay, and I'm sure you know what transfer functions are, so I'll not describe them here. I have written transfer function as S, but instead of S you could substitute j omega. So S is the Laplace variable, which when written in terms of frequency is just j omega. Okay, so this transfer function of the system, if the transfer function of the system is a of omega or a of s, how does it affect the spectral density of the noise that is being inputted to the system? The answer is the equations are here. So basically, the power of the noise gets transformed, and basically, the power of the noise is multiplied by the square of the transfer function. Okay, or another way to say is the RMS values of the noise is multiplied by the gain of this transfer function. Okay, if you have, let's say, three systems here and each of them is a filter, then what happens to your signal, the added signal? So the signal at this point is going to be A1 times Vn1, right? The signal at this point is going to be A2 times Vn2. The signal at this point is going to be A3 times Vn3. Okay, so those are the RMS values. And when you add the signal up, what happens? You are basically adding the power of the signals up. So you square those RMS values, add them up, and then you take a square root and you get the output RMS value, or the output spectral density, root spectral density. Hope that makes sense.